Dear students, let us continue our video lectures on Advanced Digital Signal Processing course. Let me share the screen. In this video lecture, we will be discussing on Discrete Fourier Series. So we have seen in the previous classes the Fourier representation or frequency domain representation for different time domain signals. Okay. Now, we give a brief idea of what we have discussed and then connect them to discrete Fourier series that we will be discussing in this video lecture. So the signals in time domain so far we have considered are continuous time, periodic signal, okay, and discrete aperiodic continuous time signal, and aperiodic discrete signal. Discrete time signal. For all of these things, we have seen what transformations, okay, will give us the frequency domain representations. Okay, so what were the transformations for periodic continuous time signal? We apply continuous time Fourier series representation to get the frequency coefficients Ck, right? Similarly, okay, similarly for aperiodic continuous time signals, we apply continuous time Fourier transform, okay, to get the frequency domain representations x of j omega, right? Since this is a periodic signal, you get x of j omega here, okay, which is continuous here. Okay, periodic signal will give rise to discrete coefficients. And aperiodic discrete time signals, we apply discrete time Fourier transform to get the frequency domain representation x of e power j omega. Please note that it is aperiodic, we get continuous representation frequency domain. However, this is also periodic due to the nature of discrete exponentials, right? And please note that a periodic signal, a continuous time signal, will give rise to discrete coefficients. In this similar manner, now we will investigate what kind of Fourier transform equations are required for getting the frequency representations of periodic discrete time signals. Okay, these discrete time signals, periodic discrete time signals, frequency domain representation is also is not only for understanding the frequency representation of periodic discrete time signals, but also it enables us to understand later a very important frequency domain representation of aperiodic signals as well, referred to as discrete Fourier transform, right? Which is very well known and widely used in all computing platforms or computing algorithms for frequency domain representation of discrete signals. Okay, so this itself will give rise to discrete Fourier transform definition and discussion. So what we here discuss is for the periodic discrete time signal to have frequency domain representation, we will apply discrete time Fourier series, and this gives a set of discrete coefficients because in discrete time it is periodic. We get discrete coefficients x tilde of k we represent here, right? So let us see now how to arrive this discrete time Fourier series equations. This has good analogy with respect to the continuous time Fourier series representation. So let us explicitly write the continuous time Fourier series expressions. If we have a periodic signal x tilde of t in time domain, right? So x tilde of t be periodic. In time domain with period t. Okay. Then to get the frequency domain representation, what do we do? Is to find out the correlation of to get the frequency domain representation of this periodic signal, continuous time signal, we find out the projections or the correlations with respect to the continuous time complex exponentials of nature k omega naught t, right? And how to find the projections or correlations with respect to them over time is through integration. Okay, so minus t by 2 to t by 2. Because this periodic signal, it is good enough to see its projections over a period, and it's normalized by capital T. To get the, and this integration is over dt. Okay, across the duration of a period, if we see the correlation with respect to the complex exponential of k omega naught frequency, what we get is the corresponding frequency domain coefficient ck, right? And this is the frequency domain representation for a periodic continuous time signal, right? And we can see that here omega naught is equal to 2 pi by capital T, where t is the period of the signal x tilde of t, right? And this is the fundamental frequency. And these are the different frequency components of it. Okay, frequency coefficients in frequency domain, right? And now you can see that these frequency domain coefficients will be separated by omega naught. Okay, because this ck represents the strength of k omega naught frequency, k omega naught frequency, right? And this is aperiodic. Okay, aperiodic and discrete coefficients. Aperiodic frequency representation. Domain coefficients. Okay. Right. Of signal x tilde of t. Okay. So now let us write x tilde of t. This is the synthesis equation. Okay. From we have analyzed here the frequency content of signal x tilde of t, and now we can reconstruct back the signal x tilde of t from these frequency coefficients through projection of inverse of these basis functions. Here it is minus, and here we can write j k omega naught t, right? So if we find the correlation of the corresponding coefficient ck with respect to the complex exponential e power j k omega naught t, okay, across all the possible values of k ranging from minus infinity to infinity, what we get is the time domain representation of the periodic signal x tilde of t, right? So now let us, in the light of these equations, let us see how to write now the frequency domain representation of the discrete periodic signals. Okay, right. So let us see if x tilde of n is periodic signal, discrete periodic signal. Okay, then what shall happen with period? Since this is discrete periodic signal, its period is also is an integer. Okay, with period n, then then omega naught defined by 2 pi by capital N be fundamental frequency. To express the frequency content of the signal x tilde of n. Okay, that is x tilde of k. Fine. So now let us see in similar lines with the above expressions, how do we write the frequency domain representation of the periodic discrete time signal. So before we move on, let us bring out the analogy between the time period t here and the period n here. Okay, so roughly you can see that the this is the continuous time period signal, continuous signal, time signal repeats after time t, whereas the discrete signal repeats after n number of samples. So you can see that the omega naught here can be will roughly replace. Okay, will roughly replace the expression here in omega naught. Okay, while this small t is being replaced by n into capital T. Okay, so and this in some sense we can absorb this 1 by t. Okay, this t in the side, so that t into ck, that is the like roughly in terms of the coefficient taken at integer samples, that is x tilde of k. Okay, so given these details, let us write the expressions of discrete time Fourier series and try to bring in further analogy or the derivation of those equations. So let's now consider x tilde of n with period capital N. Okay, so we can write x tilde of k, that is frequency domain representation for this discrete periodic signal, as x tilde of n correlated with discrete complex exponential now with k into 2 pi by n. Fine, this is a kind omega naught equivalent to omega naught into n, right? And this, since we have dropped the normalization factor n here, let us not bother about it even here. And this summation over n equal to 0 to n minus 1, okay, over the duration of n samples over a duration of 1 period will give rise to corresponding frequency at k, right? This is in some sense analogous to, okay, this is some sense analogous to t times ck. Okay, and let us write the synthesis equations now. X tilde of n now, if we wish to write from x tilde of k, right? So what do we consider here? We consider here the inverse of these basis functions, okay, which are seen here. Inverse of these basis functions, which is e power j 2 pi by n into n into k, right? But summation should be on what? Summation should be over k equal to 0 to n minus 1. And it is not from minus infinity to infinity. And there will be a normalization factor 1 by n. Since we have observed a kind of normalization factor in this expression, okay, there will be a normalization factor in the other expression, x tilde of n. Why summation is from minus 0 to n minus 1 for the frequency is because there is a difference between the discrete complex exponential and the continuous time complex exponentials. What is the main difference? These continuous time complex exponentials are not periodic, okay, in k, whereas these discrete exponentials are periodic in k. What do we mean by that? Say if we denote these discrete exponentials as, say, w and k. So let us write with this as either w and k. Okay, so or e power j k into 2 pi by n into n. See, this periodic, these exponential basis, discrete exponential basis are periodic with what period of k? Periodic in k we have written here, right? What period of k? We can see that these are periodic with j 2 pi by n into n, okay, k plus n. Okay, they will be exactly same when k is, okay, k is equal to k plus n, right? So it is written into like sum over all k, and it's not necessary, or it should not be summed over all k. Only one period of like 0 to n minus 1 are the distinct possible frequencies of a discrete complex exponential. Okay, this implies only n minus 1 or n, sorry, including 0, there are only n distinct frequencies terms. Okay, ranging from 0 to n minus 1, k ranging from 0 to n minus 1. Those are only considered for synthesizing, okay, x tilde of n, right? Please note that this is not the case in the continuous time exponentials. So to write here n into k plus n, okay, both are same, right? Yeah, if you would like to put here, we can put here. Please note that it is not the same for continuous time signals. That means e power j, okay, 2 pi by t into t into k, sorry, into k, okay, e power j omega naught t, j omega naught t into k, okay, k is not equal to e power j 2 pi by t k plus t. Okay, in fact, this is ridiculous because capital T is, okay, it need not be an integer. Okay, and what we get is the frequency coefficients, they're all integers. Okay, not an integer. Okay, so in frequency domain, it is periodic in time domain, but not in the frequency domain. Okay, please, that can be even easily noted from here. This is a periodic here, right? So that's why we are summing here from minus infinity to infinity the whole frequency content to get back or reconstruct the signal over a given period, even over a given period. Okay, so here t may range from, okay, 0 to capital T. Okay, fine. Or minus t by 2 to t by t. Okay, whereas here to synthesize the content of the time domain, what we need is only one period of frequency domain information or the frequency coefficients, right? This is due to the periodicity of the complex exponentials in frequency domain. Okay, so you can see that these exponential places are periodic with k even. Okay, and hence you can write like this, right? So this is the definition for synthesis and analysis equations of the uh, discrete discrete Fourier series. Okay, this is the synthesis equation. This is analysis. Synthesis equation of DFS Fourier series. Okay. Right. Okay. So now let us see whether these equations, which we have written them here, will they serve as the analysis and synthesis equations? Okay, it is very clear from the expression from this first equation that this gives the period frequency content at 2 pi by n times k frequency for x tilde of n, right? Given this information and now back projecting with complex exponentials of this, will that give the signal x tilde of n? This can be easily verified through a small set of mathematical tricks. Okay, so let us take the expression 2. So you can consider them as 1 and 2 if we wish. That is synthesis equation. Let us consider and let us see. So we have here synthesis equation x tilde of n is equal to 1 by n summation over x tilde of k e power j k 2 pi by n into n small. Okay, so n ranging from k ranging from 0 to n minus 1. Okay, so now let us take this right hand side. Okay, so and substitute 1 by n summation k equal to 0 to n minus 1 and x tilde of n we can substitute in terms of say x tilde of the signal m, but let us keep the running variable here as m because you have here the variable. This is a for given n. Okay, so we are writing this expression for given n. So let this variable be reserved for that given n and this be running variable m varying from 0 to m minus 1, n minus 1 for x while expanding x tilde of k here. Okay, so just to have a better understanding, this is what I'm expanding. Okay, here. Okay, so let us write this explicitly in terms of the previous definition we had minus j 2 pi n m into k and into what we have here e power minus j 2 pi n into m, right? So now let us simplify this. I'm just writing the let me write here explicitly. This is the right hand side. Okay, right hand side. Okay, so if I get the left hand side, then I think we are done. That the expressions that we have written gives us the analysis and synthesis equations for discrete Fourier series. Okay, so now let us start simplifying. So bring m outside and k inside. Okay, I think there is small mistake here. This is n. Okay, so let us yeah, m equal to 0 to n minus 1, x tilde of m, okay, summation over k equal to 0 to n minus 1. Okay, so exponential of plus and minus j 2 pi by n into k into n minus m, right? What is this summation? What is this term now? If you see this term, when you sum over for all the exponentials, okay, for any integer value n not equal to m, that is n minus m being an integer, if you sum all the exponentials, okay, for k equal to 0 to n minus 1, they will be equal to 0 because they sample at regular intervals of, okay, of a sinusoid, okay, of some sinusoid of some frequency, okay, and this sum, it can be shown that it is equal to delta times n minus m, sorry, n minus m. In fact, it is equal to capital N times delta times n minus m. This you have seen in the derivation of convolution to correlation, okay, also probably in Parseval's theorem, right? So you will be sampling here at regular intervals, okay, of one cycle or more cycles, which sums to 0, okay, if n is not equal to m. If n equal to m, what does happen? If n equal to m, then this is 1, you are summing over n times 0 to n minus 1 times, that is n times. So it is n into delta n minus n. Okay, so this summation is equal to n if n equal to m and 0 if n not equal to m, right? This you should be clear. This summation, so if you want, you can specifically write that, okay, the summation is equal to n if n equal to m, okay, 0 else, okay, that is n not equal to m. Okay, this you should remember or you should be clear. Right now, what is the answer? So let us write this now. Summation x tilde of m is equal to 0 to n minus 1 and n, let it be here, okay, and there is 1 by n also here, okay, so let 1 by n is here, okay, and into delta of n minus n. What is the delta of n minus m? Summation over m equal to 0 to n minus 1. It is simply n equal to m, it is 1, otherwise 0. So delta of n. So we are able to get here the right hand side, right? So this is the R LHS. Okay, so hence it is of our expression. Okay, so thus it proves the definition that we have taken for discrete Fourier series. Okay. Thus we define discrete Fourier series pair. Okay, yes. Okay, x tilde of n. Let us write here. X tilde of k, that is frequency domain representation of periodic signal x tilde of n by correlation with complex exponential, okay, over 0 to n over a period is x tilde of k, right? Similarly, x tilde of n you can get back from this x tilde of k, okay, by correlation with inverse of this complex exponential, discrete complex exponential basis are over again a period, because it's periodic in frequency domain as well, okay, with a normalizing factor of 1 by n, right? So these are the analysis and synthesis equations. Analysis means what analysis? Frequency analysis, okay, and time domain synthesis. Okay, synthesis equations, right? Yeah. So now let us solve a simple problem to understand how to find discrete Fourier series or representation for a given signal. Okay, a given periodic signal. So let us take a periodic signal. So let us take periodic signal x tilde of n. Let it be a discrete impulse train. Okay, n minus kn or pn. Okay, just to have a variable that is different from frequency domain variable. On t equal to minus infinity, infinity. Okay, so you can see that this is a example. Okay, so this is a discrete. So you have here. And so on it keep going. Okay, it keep going even here. Okay, so this is 0 means 1, 2, 3. Okay, so in fact it is n. Okay, this is 2n, 3n, and so on, because it's periodic with period n. Okay, and this is so this is one period of what the signal 0 to n minus 1. Okay, this is one period of the signal, right? This is the signal we have considered x tilde of n. Okay, so it's a impulse train, okay, in time domain. Now let us see how to find out its frequency domain representation. Okay, it's a periodic impulse train. Okay, so now let us see periodic impulses. So so how to find x tilde of k? X tilde of k is simply what this expression says is, and you need not bother about the whole range, just look at only one period, that is n is equal to 0 to n minus 1. Okay, delta of n, because in this range if you see it is only delta n, signal is delta n. Okay, if you see whole signal then it is this, whatever we have written, e power minus j 2 pi n nk, and this is equal to 0, 1, this is 1. Okay, however, if you want to represent this signal, okay, so x of k equal to 1 for all k, right? For all k. Right. Okay. Right. So n equal to 0, and then this is what? Yeah. And this is one for all k, right? So now if you want to represent the signal, then it is an impulse train in frequency domain as well, right? Because it's periodic in frequency domain. Okay, it's all ones. Okay, so the signal that if you wish to represent in frequency domain, okay, x tilde of k, then it is 0, 1, 2, 3, okay, 4, up to some n. Assume that if this is n, okay, let us break it somewhere and then say n, okay. So if this is n, the scale is not same, but let me see if we can make the scale also same. So if you want to make the scale also same, okay, so this is 0, 1, 2, 1, 2, 3, yeah, this itself is n, let it be. Okay, in that case, how will be the signal? Signal will be 1, okay, 1, 1 here, okay, and then it will repeat again here, okay, and so on. So k, this is the axis is k, okay. So x of k itself is now delta of, okay, delta of, so you can write simply 1, okay, for all k, right? Okay, this is one example. Similarly, you can see other examples. Let us take one more example before we close this discussion. So let x of x tilde of n is equal to 1. Okay, for 0 less than or equal to yeah 4, n less than or equal to 4, and 0 for 5 less than or equal to n less than or equal to 9. Okay, so the signal is of period 10, okay, but having this kind of magnitude, that is x tilde of n is periodic with period 10. Okay, so that is n equal to 10, n equal to 10. Okay, and this is the signal, right? So what will happen if you sketch x tilde of n? It will be 1 for some time and 0 for some other time, and then keep repeating after 10 samples. So 1, 2, 3, 4, 5 samples. 0, 1, 2, 3, 4. Okay, and 5, 6, 7, 8. Okay, 9. Okay, again from this sample it repeats. Keep repeating. 3, 4, 5. Okay. So same in this direction. So I am not sketching it, but it will be same in this direction. Okay, so 10, 11, 12, 13, 14, and so on. Okay, this is all zeros. 15. Keep repeating at 20 again. Okay, so 15, 16, 17, 18, 19, 20 roughly here. Okay, 20, 21. Okay. And okay, so this is the signal x tilde of n. If you want to analyze the signal as given by discrete Fourier series definition, it is good enough to look at the one period, 0 to n minus 1, right? So hence this is one period. Okay, so now let us write x tilde of k for this signal. Okay, so let us write for yeah, this signal x tilde of n e power minus j 2 pi by n to nk. Let us write for a general say this is capital N, right? So up to small n1. Assume that the signal x tilde of n is 1 for up to cap n1 and 0 for the rest of the duration. Okay, for that let us write and then substitute finally n1 is equal to 4 in this case. So that we will have a general expression. Also, we can have the specific answer. N here is equal to, by definition, n is equal to 0 to n minus 1, right? Okay, so let us discuss, let us substitute here n equal to 0 to n1. It is non-zero, that is 1, value is 1, okay, because we have taken n1 equal to 4, e power minus j 2 pi by n into nk, right? So let us simplify this. While simplifying, we can use the geometric progression here, because this can be written n equal to 0 to n1, okay, e power minus j 2 pi by n into k power n, okay, because it's keep n keep increasing by 1, okay, so it's like a power 0 plus a power 1 plus a power 2 and so on. Okay, this can be written as what? 1 minus e power minus j 2 pi by n into k whole power n 1 plus 1, that is number of non-zero terms here, by, okay, 1 minus e power minus j 2 pi by n into k, right? This you can simplify like this. And this can be better expressed in sinusoids. Okay, so let us write this explicitly. By taking e power minus j, so let me write with different color just to have a better contrast. E power minus j 2 pi by n, okay, into k into n1 plus 1 by 2, let us take outside, okay, from numerator. And from the denominator, let us take e power minus j 2 pi by n, okay, into k by half. Let us take this outside from denominator. And then what we have is e power j 2 pi by n k, okay, n1 plus 1 by 2 minus e power minus j 2 pi by n k n1 plus 1 by 2 by, please see what is the numerator term and what is the denominator term now. E power minus, sorry, e power j 2 pi by n into k by 2 minus e power j 2 pi by n into k by 2 minus sign, right? So now what is the numerator term and what is the denominator? So we shall write explicitly in the next slide. So the first, let us write the first part of the simplification. Okay, what is this? So half and goes out. So it will be simply e power minus j 2 pi by n into, okay, n1 by 2 into k. Okay, anyway, k is there, right? This is the numerator term. And now what is this numerator and denominator terms? 2j into sine of this. Okay, similarly 2j into sine of this. So 2j gets cancelled. Anyway, let us write 2j into sinusoid of what? Sine theta. Okay, e power j theta minus e power minus j theta. Oh, e is nothing but sine 2j sine theta. Sine 2 pi by n into n, sorry, k into n1 plus 1 by 2. Right? That's the numerator term. By the denominator term is what? 2j into sinusoid sine of 2 pi by n into k by 2 into 1 by 2. That's all. Okay, k into k by 2 or k into 1 by 2. Right? This is the denominator term. So this in fact is referred to discrete sinc. Okay. So for a continuous time signal, sinc is sine pi t by pi t. Okay. So that you have seen for the continuous time signal. Whereas discrete time signal, the sinc is this. Okay. So you can see now x tilde of k is e power j 2 pi by n into, okay, k into n1 by 2, fine, into sine of 2 pi by n. Sorry, let us write this. Sinc of, okay, let us write in terms of sinc now. 2 pi by n, right? So sinc when you write, in fact, we need not write 2 pi here. Okay, let us write sinc t, you can write, right? So in that way, you can write, you need not write omega naught, but let us write here explicitly itself. So let us write sine 2 pi by n into k into n plus 1, okay, by 2 by sine 2 pi by n into k by 2, right? This is what is x tilde of k, right? Okay, so now let us see if we have a signal which is aperiodic and looks similar to x tilde of n over one period, then what is our discrete like discrete time Fourier transform? That is x of e power j omega. If we find for, let x of n be is equal to, let x of n be equal to, right, only one period of x tilde of n for n 0 less than or equal to 9. Okay, then if you wish to write x tilde of n, sorry, x of e power j omega, so what do we write it? So if you remember, it will be equal to e power, I am directly writing here 2 pi by n. Okay, 2 pi by n is this, the length of the signal here. Okay, length of the signal n equal to 10, length of signal. Okay, here n is not period but length of the signal. Okay, n means of x of n. Okay, right, 2 pi by n into e power a sinusoid sine of, okay, e power j omega n we would have had. Okay, x tilde of n, what is the expression there? So if you remember the expression, x of e power j omega is equal to x of n into e power minus j omega n and summation over n, small n. Okay, and hence this 2 pi by n will be captured in omega, right? So it's omega, and k also gets captured. 2 pi k by n gets captured in terms of omega, in fact. Okay, so here for omega into n plus 1, okay, by 2, right? That's what you can see in the numerator, while the denominator is sine, okay, omega by 2, because this whole thing is captured in omega by 2, right? This is again sinc. Okay, signal. So we will see little more elegantly. So let us write this part also little carefully. E power minus j omega, this whole captures in. So let me write. So here, which captures in 2 pi by n into k. Okay, this gets captured in omega. Please see the expression. You can just redo the substitution and the simplification from the definition. Okay, but after doing this, you can see that the analogy is this. Okay, e power j into n1 by 2. Okay, so you can see that. And this is what you get for x of e power j omega. So it looks like, okay, it appears that the x tilde of k is sampled version of x of e power j omega, right? The samples are at omega equal to 2 pi n by k. Okay, so in the subsequent classes, we will see whether is this true for any signal x of n, or x tilde, like can it be considered as a period of x tilde of n? Okay, and hence the samples of like one x tilde of k, okay, that is samples in frequency domain, can they be considered as the samples of the spectrum x of e power j omega? That we will discuss in the next video lecture or subsequent video lectures. X tilde of k, can these be looked at, okay, samples of x of e power j omega, okay, at omega equal to 2 pi by n into k. Okay, can this be looked at this as the samples of this, right? As we have seen in this particular example. Okay, so in this particular example, both you can obtain from the definition and relate, but however, is it in general true? Okay, or if we sample in frequency domain, what will the spectrum, discrete Fourier series spectrum, will it be exactly same as the sampling the discrete time Fourier transform? And subsequently, what is the consequence? Does this also imply, right? Does this also imply, okay, x tilde x of n being a period of what? A period of x tilde of n. Okay, if so, if implied, if so, when? Okay, if so, when? Okay, when means does it hold for all n? And is there any condition on the number of samples in frequency domain? Okay, etc. We'll see these two equalities or the related discussions in the next subsequent video lectures. Thank you.